Of the climate system and come up with some idea of resolution through these, but still, even in the fourth assessment report, we're at 110 kilometers in the atmosphere. There'll be some contributions on the 100-year simulation timescale in the fifth assessment report that were 50 kilometers. But the point here is that quasi-uniform simulation, basically using the same resolution over the entire sphere for all the model components, is a very hard way to get the high resolution. And so, right, okay, so one last slide to motivate this. So, you know, I think maybe the Indian monsoon is sort of the canonical example of why we need a multi-scale modeling approach. So within the Indian monsoon region itself, there are multiple scales. There are scales from the topography. There are scales by the contrast of the land sea mass. And clearly, if you're interested in the Indian monsoon, you want the majority of your computational resources over the Indian monsoon region. But we cannot understand the Indian monsoon in isolation. It has important large-scale drivers, right? We have, you know, if we think of the Indian monsoon, we think of the drivers from the tropics. Clearly, ENSO has an impact on the Indian monsoon. Then embedded in ENSO, we have the Manchurian oscillations that have an impact. Then if we look towards the extratropics, we have snow cover and other large-scale features in the extratropics that impact the Indian monsoon. So what we need is a way to be able to put the majority of the computational resources in our domain of interest, but put enough computational resources in the large scale so we get the right connectivity between our area of interest and the rest of the sphere. So this boils down to three things, and so I'm going to come back and touch on this again and again, but there's sort of, in my view, three requirements that we have to meet in order to do a good job at multi-scale modeling of the climate system. First, we need a multi-resolution mesh. I'm going to talk about that today. Then we need a simulation of the primitive equations and Naylor-Stokes equations that are a discretization of those equations that are valid with multiple scales present. And then finally, we need scale-adaptive physics. Because, you know, the situation I outlined here, you know, possibly we could run without a convective parameterization in the Indian monsoon region, but clearly we would need that convective parameterization through the rest of the tropics and possibly for part of MJO. And so we need a scale-adaptive physical parameterization here, cumulus parameterization that knows when to turn itself off and when to turn itself on. So the purpose of this presentation is to describe and go through some test cases to evaluate our ability to do multi-scale simulations of the primitive equations. And I'm going to keep coming back to these 3 points. And I think next in the presentation, we're going to talk about how we design a multi-resolution mesh, how we have a global mesh that has multiple scales within it. So really, this is the easiest part of the whole deal. Making the mesh is no big deal, but from the outset, we need to make a pretty big decision. And we need to decide whether we're going to have a conforming mesh or a non-conforming mesh. So we're going to have a mesh that slowly varies in resolution, or we're going to have a mesh that makes discrete jumps. And there are pros and cons to both of these, and I think in the end, both are actually viable approaches to multi-scale climate modeling. This is really a fork in the road here. You pick one and you're sort of tied to that for a very long time, and we've chosen this for better or for worse. And so I'm going to talk about how we build nice conforming meshes. So the difference between conforming and non-conforming is, so on a non-conforming mesh, we have this long edge has one cell on one side and has 3 on the other. And so we have what we call hanging nodes. So a conforming mesh, every edge of every cell is uniquely shared by 2 cells. So there are no hanging nodes, and every cell is topologically exactly the same. And this turns out to be very important in the multi-scale numerical method that I'll talk about tomorrow. Okay, so the route that we've chosen are these centroidal voronite tessellations. I'll talk about their construction and properties. So first, to give you sort of a visual cue of what we do with these meshes. It turns out there's a very easy way to specify where you want your computational resources. And so these are meshes that we have used to actually do simulations. So here's a place where we wanted to put enhanced resolution in the California current. Here's a place where we want to do enhanced resolution for climate change studies in North America. And here, for this ice sheet application, and we're not going to talk about ice sheets, but it certainly is a pretty mesh, we put resolution in ice streams where the majority of the ice flows out into the ocean. Okay, so spherical Voronoi tessellations is clearly a mouthful, not something that kind of rolls off the tongue. So I'm going to kind of walk you through it and explain to you why we use such a complicated name. So first, tessellation is simply a fancy word for a non-overlapping grid. So we're going to, and in particular, tessellation has a connotation of two dimensions. So we're going to tessellate some two-dimensional surface, and in this case, we're going to tessellate the surface of the sphere. So that gives you the S and the T. Okay, so now something that it might be new. So Voronoi, it's a very special kind of tiling. It's quite beautiful, and it's quite intuitive. So think of having some surface, and on that surface, put some grid points. And so now you have a surface, and you have some dots. You just lay them out arbitrarily. You have some dots on your surface. And now what you do is you go to every point on your surface and you find the closest grid point. The closest, we call them generators. You find, for every point on your surface, you find the closest generator. And you assign that point to the closest generator. And you end up, when you then draw the boundary of every generator, you have a Voronoi mesh. So, for example here, this boundary basically delineates the space that's closer to this generator than to any other generator, and this region does the same for this generator. Okay, so that's the Voronoi bit, and then the centroidal is the magic. It's the magic that allows us to build a mesh like this. Okay, so more about this. So here we've taken a two-dimensional space, and we've randomly populated it with these small dots. And then we've gone through this definition of Voronoi, of a Voronoi tessellation, and we get these boundaries. So these boundaries, so for instance, this boundary here is the set of all points that are closer to this generator than to any of these other small dots. So the centroidal piece is we want that generator to also be the center of mass of this region. And so the center of mass is some density-weighted interval over the Voronoi region. And if we just say a uniform, so we get to pick this, and this is what's going to allow us to make these variable resolution meshes. But if we pick this just to be uniform, then in this case it reduces to the center of area. And if we do that interval, we get these open dots. So here's the Voronoi generator, here's its center of mass, and then what we do is we simply move the generator to that point, we draw the Voronoi diagram, and we iterate. And if we do that, we end up with this very nice uniform mesh. And the difference between this mesh and this mesh is the Voronoi generator is also the center of mass for that cell. Can I get this moving? And so here what we've done is, so remember that blue, we've got that blue region. It's going to have a high density inside that blue region, and it's going to have a low density outside that region. And then if you go through this iterative procedure that you can write a little MATLAB code to do, what you see is it moves your points into your high resolution region. It turns out that it converges exponentially slow, and so all the fun part's over, but it's still actually iterating. You can see little lines, cell edges changing in length. But I think we're good. So this density function is yours to choose. And so you pick your application, and you pick what resolution you want in your region of interest. You pick what resolution you want for the rest of the sphere, and you'll be able to write down analytic form for the density function. And you can generate a mesh that has the resolution you want in the parts of the domain that you're interested in. And so there's two bits here. This is basically the mathematical expression of what I just said in Rho. So again, we get to pick this density function, and xj and xi are just two different points in our region. You can think of, let's just say, for example, xj is our high resolution region, and xi is our low resolution region. And the h here is your grid spacing. And so you specify that. You say, I want 10 kilometers in the Indian Monsoon region, and I want 80 kilometers elsewhere on the sphere. And so when you specify that, that specifies the ratio of your densities. You write that down. You go through this iterative procedure, and it pops out the mesh you want. It so happens that the power you raise the density depends on the space that you're in. In our case, we're in 2 space, so this is the density raised to the 4th. The other thing that's really important here is that the mesh quality is guaranteed to improve as you improve resolution. And what you see here is, so oftentimes these meshes are referred to as hexagonal meshes. They're not really hexagonal meshes, but you can understand why, because the preferred polygon is 6-sided, and in the limit of infinite resolution, you actually you can prove that you end up with all perfect hexagons. So here's some example of meshes that we use every day, and what we actually did with these. This figure comes from a paper we wrote using the shallow water equations. We simulated the shallow water equations on a quasi-uniform, varied by a factor of 2, and below see the change in resolution, 0, 4, up to 8, up to 16. These are typical meshes that we use every day. They have a very smooth transition between the low and the high resolution, and I'll show you simulations today, I think, of a by 8, and tomorrow we're doing ocean simulations with by 16. So by 16 is actually pretty big. It means that in the North Atlantic, you can get down to 4 or 5 kilometers resolution, and then you have 80, 90 kilometer resolution over the rest of the sphere. So these are pretty conservative meshes, but the meshes can be as conservative or as exotic as you want. And so these meshes were actually generated from an analytic density function. We wrote down a closed form of our density. These meshes here were actually, this mesh here is a density function that's based on distance from the coastline. So we put all the resolution around the boundary of Greenland. And then here we've taken one region and blown it up so you can see the changes in scale. This mesh here, we generated the density function based on the kinetic energy of the fluid. So we did a simulation, we computed the kinetic energy of the fluid, we turned that into a density function, then we turned that into a mesh. So I think the last bit to say about the meshes, and that is how we implement them on a massively parallel machine. The nice thing about using an unstructured mesh is that you get a tremendous amount of freedom about how you do your domain decomposition. And we use a fairly common tool, Metis or Power Metis, to take our global grid, and each of these are blocks, and we assign each of these blocks to some computational node. And then here's a blow up of somewhere on this figure where here are the cells on a processor, and then we've shaded. Here we're using a halo 1. In our simulations, we typically use a halo 2 or 3, depending upon what we want to do. But then we have a halo region. And as Jimmy showed, and as I think I'll show tomorrow this scales well. You know, on a typical day-to-day, we'll run our ocean model or atmosphere model on a couple thousand processors, and we've done simulations up to 10, 20,000 processors. Okay, so I want to close there with talking about the meshes and try to convince you that we can actually do something useful with them. So the first thing I want to talk about are these aquaplanar simulations. And for those of you who might not be familiar with aquaplanar simulations, they're an idealization. So we have the sphere. We assume the entire sphere is covered with ocean, and furthermore, we make the sea surface temperature zonally symmetric. Here's a snapshot of an aquaplanar simulation, and then here's a bi-8 mesh. And so all of our bi-8 meshes are going to use 30 kilometers in the high resolution and 240 kilometers in the low resolution. Then you might ask, why in the world would we want to evaluate our multi-scale mesh method in this aquaplanar simulation? And that's because all of the forcing is symmetric, and so we know that the climate of the system should be symmetric. And therefore, if we put down this multi-scale mesh, any deviation from zonal symmetry is error. So this is a very easy way to assess it, to evaluate the quality of our simulation. We're going to do a couple things. I told you already, we can assess error by just the zonal asymmetry. We're even going to be cleaner than that. Here's a set of resolutions. So 240, all these right here are globally uniform. So going from 240, down by factors of 2 down to 30. Now we're going to have one variable resolution simulation that goes from 240 to 30. And it's going to look, this is the mesh, so here's our high resolution region. This is 60 degrees by 60 degrees. Okay? So then what we can do is, we can compare this simulation to its 240 and to its 30 to see how this simulation does compared to its quasi-uniform counterparts. The other point is, all these simulations were done with the exact same executable, the exact same parameter settings, and the only parameter that changed in these different simulations is one parameter, the hyperdiffusion. On the momentum equation, we use a monotone transport scheme for a scalar, so we don't need any ad hoc closure there. And it just reduces by a factor of 10 every time we double the resolution. And for the scaled mesh, the local viscosity takes on the value based on the local grid spacing. And all the other parameters are exactly the same. And the other thing to point out here is that this is a full physics CAM4. So the forcing, the boundary is idealized, but the physical parameterizations are exactly what was used in IPC assessment reports from this model. So the first question we ask is, how we deal with the fluid dynamics? Can we represent the fluid dynamics well in this global high resolution region? And so what we did is, we computed the kinetic energy spectrum in this high resolution region. Then we took our global 30-kilometer simulation and we pulled out this region, and we computed the kinetic energy spectrum over that region as well. And we plotted them both, and they lie directly on top of one another. And in fact, models should show a transition to the mesoscale around 300-400 kilometers. And both our variable resolution and our global resolution show this transition to the mesoscale, to the -5/3 at 400 kilometers. In fact, these two are identical. So the fluid dynamics within this region is identical to the fluid dynamics within this region from the global 30-kilometer simulation. And we've done other tests that have convinced ourselves that from a fluid dynamics point of view, this multi-scale approach works extremely well. And so here is one more example of that. This is from the global 30-kilometer, this is from the global 240, and this is from the global resolution. These are Hofmahler diagrams, so we have time going down and longitude going to the right. And these are filtered to pull out the Kelvin wave. And we can see that these Kelvin waves are propagating through the mesh transition zone as well as we see those Kelvin waves in the quasi-uniform simulation. But it turns out that while we were doing a very good job with the fluid dynamics, the physical parameterizations aren't scale adaptive. The physical parameterizations act different with different resolutions. And in fact, for the moment here, just ignore these middle panels, okay? And just pretend that they're not there. This is total precipitation and column integrated water vapor from the global 30 and from the global 240. Now, so water vapor is a large-scale quantity, and it's a quantity that we would expect to be insensitive to our model resolution. So we can see that the 240 and the 30 actually have dramatically different column-integrated water vapor, particularly in the tropics. And in fact, the 30 kilometer wants a moister climate than the 240. And we've seen this for decades, but we've never had a multi-scale model that put these scales into a single simulation, and so we could somehow maybe ignore it a little bit. But if you do put it into a single simulation, you get actually what you should expect to get. So remember, in the tropics, we have easterly, so the winds are going from right to left. And so when the fluid's out here, it doesn't actually know there's a patch of 30 kilometer resolution in this circle. And so it equilibrates to exactly what we get in the 240 kilometer resolution, so low resolution. As the fluid comes into a high resolution, it begins to realize that it wants to be in a different climate. It wants to be in the climate that's moister because it's a 30 kilometer resolution. And you can see it moistens. And then it carries that signal with it out of the region, and so finally it comes to terms that it's no longer in the high resolution region, it's in the low resolution region, it dries out, and it begins to act like the 240 kilometer simulation as well. And we see that signal in precipitation. So the model dynamics are adaptive, they are multi-scale, but the model physics are not, and that's a huge problem. I'm going to skip over that. It says the same thing. And so this has actually been published in the literature, but these are just a host of different models at different resolutions, and this is zonally integrated water vapor. There's no sense of, and so this is at the South Pole, and this is at the equator. There's no sense of convergence in, this is cloud fraction. And these are all from global quasi-uniform simulations. If the global quasi-uniform simulations aren't giving the same results at different resolutions, then we'd be hard-pressed to expect a multi-scale model to do any better. So these results are published. I think they're sort of in the early release. I have a copy I'd be willing to give out, but it's also on the Journal Climate website. So AMIP simulations, these are ongoing, and I think we're actually going to have to end up doing most of these simulations again. But we did the exact same thing. So AMIP simulations, for those of you that might not be familiar, so they're real world. So we have land, we have ocean, we have real topography, we have different categories of vegetation, but they're not coupled simulations in the sense that we specify SST and we also specify sea ice coverage. They are one step before a fully coupled global climate simulation. So the first thing you have to do with a model, with a new model like AM past atmosphere, is run it in quasi-uniform mode. And now, since we're actually in a real-world configuration, we can compare to observation. So we can compare to NSEP, and we can also compare to the spectral element model, which is the default model within the community atmosphere model. And so here is zonally integrated temperature, and here is zonally integrated zonal wind. The only thing I want to say here is that this does look like planet Earth, and it's doing a fair job of reproducing the observational data set. And then these are the exact same two models, but now looking at, I think this is precipitation. I should have put that up there, sorry about this. And I think this is actually annual mean precipitation. So this is from the impasse atmosphere of over 30 kilometers, and this is from the spectral element. And these models have a different dynamical curve, so a different numerical method for solving the Trinity equations, but are using the exact same physical parameterizations with the exact same settings. There are some differences. We're not getting as much rainfall over Africa. Our ITCC is a little weaker, particularly in the Atlantic. They do show many similarities. This model has been around for a couple of decades. This is the first ever global 30-kilometer simulation we've done with it. I'm happy to where we're at. I think we can do better. But for the point of today's presentation, what I want to convince you of is that this does have some utility in terms of a multi-scale model. So here's a global 30-kilometer simulation, ANIP. Here's a global 240-kilometer simulation, ANIP. And then here's our multi-scale simulation where we have 30 kilometers in this region here. And what you'll see is that, just pick out the storm track, right? We get an excellent reproduction of the storm track from the 30-kilometer simulation and the multi-scale simulation that is not showing up in the 240. We're also doing a little better job with the minimum in the subtropical high. You will notice that we're getting some noise out here in the variable resolution simulation. Part of this is interpolation, but part of it is because I take full blame for this. We're Ringler cut at time stepping our dissipation, and we should be Euler forward time stepping it, and we basically made a poor choice of how we're time stepping our dissipation, and that's leading to noise, which is why I think we have to do these simulations again. So what I hope I've been able to at least make a plausible argument of is that one, we have a way to produce these multi-resolution meshes, and two, we have some acceptable, certainly not perfect, and certainly room for improvement, but we have some acceptable multi-scale simulations using a pure physics atmosphere model. So what I'd like to do for the next 5 minutes, maybe 7 minutes, is to talk to you about why I think we should continue to explore this approach. I don't want to give you the impression that this is anywhere near a done deal or that it's accomplished. We're very much in the middle of exploring how the model works and how the method works and what utility it has. And so I think it's fair to ask, should we really be devoting more resources to developing this approach? So I think I'm going to give you three reasons. I think I actually have a list of 10, so I'm letting you off easy by only giving you 3. So the first is, there's a tremendous amount of resources being expended around in the international community with limited area climate modeling. We call them LAMs, limited area models. The other word that it goes into is regional climate modeling, RCMs. And so in these efforts, what they do is the community picks a region of interest, NARCAP, ensembles, and says, this is where we want to understand climate. We're going to put our computational resources in this region, and then we're going to supply some lateral boundary data to force our model. But actually, if you really think about it, the global modeling community and the regional climate modeling community have the exact same aspiration. They want to understand anthropogenic climate change. And they've only made, the only thing that distinguishes them, that distinguishes the two groups is how they've allocated their computational resources. And so now we actually have a modeling framework where both of these communities can live in one model and still make different decisions on how they separate or how they allocate their computational resources. And it turns out, it might be surprising, but it turns out that running a global model is cheaper than running a limited area model. And now you think to yourself, how in the world can that be? Well, it turns out that all of your, if you do, say, a 30 kilometer within your region of interest and you do 230 elsewhere, just take the NARCAP, it turns out that like 80% of your computational resources are inside your region of interest, which means you're only spending 20% of your computational resources to simulate the whole rest of the sphere. And it turns out that simulating the whole rest of the sphere is cheaper than having to store and read in your lateral boundary data. There's nothing worse to computer performance than having to read data off of disk. So not only is it, I think, theoretically a better approach to regional climate modeling, but it is actually also cheaper. The second is, even if you had no interest in multi-scale modeling, this is a great way to measure the quality of our physical parameterization. An appropriate physical parameterization is going to adapt with scale. It's going to change its response to the amount of, it's a cloud, it's a cumulus parameterization, right? The perfect cumulus parameterization will know to turn itself off as the model begins to resolve that physical process. Which means is that if I have a model that has different spatial scales in it, and I expect a zonally symmetric response, then I can measure the quality of my physical parameterization by measuring the zonal asymmetry. And so this test case that we put together, this aquaplanet where we put this region of mesh refinement, is actually being very well received by the folks that built physical parameterizations, because now they have a very easy to run test case to measure how well their physical parameterizations are doing when presented with multiple scales in a single simulation. And the last one, I think this is a more efficient way to build a global quasi-uniform model. To tie it back to the beginning, Matt Melcher, who's a scientist in our group, he's been at the foreground for about 20 years now doing global high-resolution simulations. So he puts high resolution everywhere. And it takes him 5 years to work through this, from generating the grid to working out all the bugs on getting a grand challenge simulation going on a new computational platform, typically rewriting code to make efficient use of that computational platform. So he's devoted his entire career to being on this bleeding edge of doing these new global quasi-uniform simulations. But if you have access to a multi-scale model, you can now resolve grand challenge scales without putting those scales everywhere. You can say, I'm really interested in North Atlantic. I'm going to put all my computational resources in the North Atlantic, and you can immediately resolve scales on traditional everyday computational platforms that you cannot resolve on the fastest computer in the world if you want to resolve that scale everywhere. So this is a great way to push our models to new scales without having to wait for someone like Matt to kind of trudge on another 5 years and push the boundary forward. So I'll leave it there. Thank you.
So you have 8 minutes, so you open to any questions. Sir, in the middle, you talked about parameterization acted differently at different resolution levels. But it is we make the parameterization to act. We make the parameterization to act, whether differently or same in different resolution levels. Because the physics will be different at different resolution levels. But you told in the middle that parameterization by itself acted differently at different resolution levels.
So we would like the parameterizations. We want the parameterizations to act appropriately, act correctly at different resolutions. And so as a process becomes resolved, we would like the parameterization to turn itself off. So what you need is what you want right there.
Yeah, before that slide.
Yeah, right there. Well, no, so what you want is for the multi-scale approach to work, you want resolved plus parameterized to be a constant. That's a minimum, and you would hope this constant is also correct. Okay? But what we're getting here is that resolved plus parameterized is not a constant. It's changing with resolution.
Okay, you talk.
Todd, one question I have: how you are ensuring the continuity of variables, atmospheric variables with variable meshes? Because at boundary.
So there is no boundary.
That means higher resolution to coarser resolution. Because numerical errors are different in both resolutions.
Let's remove the physical parameterization problem for a second. Let's say we're just doing primitive dry primitive equations. As I'll talk about tomorrow, so this cell is treated exactly the same as that cell. Every cell on the mesh is treated exactly the same. It doesn't know whether it's part of a global quasi-uniform mesh or it's in a mesh transition zone. The numerical method is exactly the same for every cell. And so that is actually the reason we chose conforming, the conforming mesh approach. Because in the conforming mesh approach, topologically, every cell is identical. And so you have at least the opportunity to have a numerical method that can then work on a variable resolution mesh. Now, it's true, and I'll show you this tomorrow, and it shows up better in an ocean than in a climate, right? If I'm resolving, so let's say this is 30, and I'm resolving scales, just hypothetically, that are 30, that have a scale of 30 kilometers. That process, let's say it's an eddy, right? That eddy can't live out here because the mesh is 240 kilometers. And so something has to happen, absolutely. There has to be a pushing, a change of the scale of motion as the fluid moves from the high resolution to the low resolution. It appears that it does most of that by itself, but I think in the end we probably will have to do something smart to make sure that change in scale of motion occurs appropriately. The advection scheme is monotone, and so that helps for sure. But the advection scheme again doesn't know about the mesh either.
Todd, as a follow-up, you spend quite a bit of time and efforts in order to create very locally, at least, very uniform meshes.
Yeah.
How important is that actually? Can you afford to not spend so much effort on that?
No. So we're using a low-order finite volume method, and so absolutely, if you were throwing a fifth-order discontinuous Galerkin method out of this, you could have a very coarse, you could have very rough, unsmooth meshes, and I think still get a nice result. But for us to get quality results, we need a smooth meshes. We actually haven't tested yet, how fast this mesh transition can be. I'll show you some pretty aggressive meshes tomorrow. I think we're okay there.
Yeah.
Yeah, so just again a follow-up, Todd. You would like to think that you treat this fine mesh and coarse mesh the same, but they are truncation error. Truncation error basically depend on two important things. One is delta x, the other is function value. So the high resolution function is actually the shape is different from the coarse resolution, and the truncation error of the delta x between the two are different. that's caused a lot of this wave refraction, and that is not that easy. I think that you would think there is no problem, but I don't think it's as easy as you would like to.
Well, I mean, I mean, using whose numerical method? Yeah. Well, no, the numerical method is important.
As a follow-up question of Amit, that you told that there will be this fine resolution, high resolutions, and the coarser resolutions that message will be identical. But when we saw that in the variable resolution, the 30 kilometer and 240 kilometer, when we go to the high resolution, there is a boundary problem. Means there is a lot of noise will be there when we are going to the high resolutions. So some sort of boundary problems is there if you are going to a X8.
I mean, so this is the reason I showed this plot, right? So if there was reflection, we would expect to see it here.
When you saw this total precipitation.
Oh, right, but that has nothing to do with the numerical method. That has to do with the fact that I made a mistake in how I'm integrating my dissipation term. I'm pairing my dissipation term with an RK3 method, which is a bad idea, right? So this actually has nothing to do with the mesh, and has to do with a very basic numerical principle that I overlooked.
So we can, okay, it's the last question. Yeah.
I just want to put your talk in the context of this observational community, most of the people here, regarding scale-aware parameterizations. So what is the role that they could play to help advance parameterization? Obviously, there's a no man's land before you can turn it off and turn it back on, in which it will work reasonably. And then there is also an area where parameterizations develop a coarser resolution. Models are not really working very well as we move to higher resolutions. So in order for this whole thing to work, for multi-scale simulations, we really need these kind of parameterizations which can transition across the scales.
I agree. So I think there are always engineering approaches that you can use first, right? So I think right now there are ad hoc approaches where we could. I mean, these models, this 30 and 240, they're actually tuned to different parameterization. They're tuned with different parameters in the CSM. And so in these variable resolution simulations, you could choose these parameters to be different. Okay, that's very unpalatable to me. That's an engineering solution, but it's a solution that could be used today to help us get results. But I mean, the community has been looking to build a good cumulus parameterization scheme for 40 plus years now, and they haven't found it. So the reason they haven't found it isn't because they didn't have a multi-scale model. They haven't found it because it's a very difficult parameterization to obtain. But I think we also need to be aware that parameterization is more than convection in the atmosphere, right? I'll show you tomorrow, right? I think we have a much better chance of doing a multi-scale parameterization of mesoscale ocean eddies, and maybe that's a place to start. But no, I guess I don't have any words of wisdom on very smart people who have been trying to solve this problem for a very long time.
Okay, let us thank Dr. Ringler for a very excellent. There may be some questions, so we can use that tea time.